Good morning. I am Chinmay and I have along with me my teammates Chandan, Aman and Kamna. We are students of Vellore Institute of Technology, Chennai. Our project is on the topic of breast cancer detection using deep learning and we are doing it under our faculty, Professor Khader Nawaz. This is our review 2 and review 3 combined. Now I would like to call upon Kamna to start the presentation.
Myself Kamna, my teammates and me are here to present review 2 and 3 of our project. Our topic is breast cancer detection using deep learning. What is breast cancer? Breast cancer is a type of cancer that originates in the breast tissue. It is the most commonly diagnosed cancer in women and the second largest causing of death among them globally. In rare conditions, breast cancer can also occur in men. Breast cancer occurs when the cells in the breast tissue grows and divides uncontrollably. These abnormal cells then form a lump or mass in the breast, which may be felt by the patient or detected by a mammogram. If left untreated, breast cancer can spread to other parts of the body, such as lymph nodes, lungs, or liver. There are different types of breast cancer, which are classified based on the location and behavior of the cancer cells. Breast cancer detection and diagnosis typically involves a combination of physical examination, imaging tests such as mammography, ultrasound or MRI, and a biopsy, which is a procedure to remove a small amount of tissue for examination under a microscope. However, these methods have limitations, such as false positives, that is when a test indicates the presence of cancer when there is none, and false negatives, that is when a test fails to detect cancer which is present. So deep learning, a subfield of artificial intelligence, has shown promise in improving the accuracy and efficiency of breast cancer detection and diagnosis. Deep learning algorithms can learn to recognize patterns and features in medical images such as breast mammograms, and then it classifies them as normal or abnormal. One example of deep learning in breast cancer detection is the use of convolutional neural networks, a type of deep learning algorithm that is commonly used in image recognition tasks. CNNs can then be trained on large data set of mammograms to learn to detect the subtle features and characteristics of breast cancer. In a study published in the journal Research, they developed a deep learning algorithm that was able to accurately classify mammograms as benign or malignant with an accuracy of 94%. The algorithm was trained over a data set of about 229,000 mammograms from over 60,000 patients and was able to detect breast cancer with a sensitivity of 90.2% and a specificity of 95%. Another example of deep learning in breast cancer detection is the use of generative adversarial networks, that is GANs, a type of deep learning algorithm which can generate realistic images based on a given input. Researchers have used GANs to generate synthetic mammograms that can be used to augment real mammograms for training deep learning algorithms. This can help to increase the size and diversity of the training dataset, which can improve the accuracy and robustness of the algorithm. So deep learning algorithms have been used in breast cancer diagnosis by analyzing biopsy images to identify cancerous cells. So it is breast cancer being common and deadly disease, which is difficult to detect and diagnose. So we have developed deep learning algorithms such as CNNs and GANs, and they have shown promising results in improving accuracy and efficiency of breast cancer detection. The reason why we have chosen this topic was that breast cancer is one of the most commonly diagnosed cancers in women and a leading cause of cancer-related deaths worldwide. Second reason is that there's high availability of medical imaging data. The field of radiology generates vast amounts of medical imaging data, including mammograms, ultrasounds, and MRI scans, which can be used to train and validate deep learning algorithms. These data sets can be accessed through public and private repositories, making it easier for researchers to develop and test their algorithms. So before we jump into a project, I would like to brief you about mammograms. A mammogram is a type of low-dose X-ray imaging test which is used to detect and diagnose breast cancer. Mammograms are primarily used for breast cancer screening in women who have no signs or symptoms of breast cancer, as well as for diagnostic purposes in women who have breast lumps, discharge, or other symptoms. Mammograms can detect breast cancer in its early stages, often before a lump can be felt, which can improve the chances of successful treatment and survival. Screening mammograms are used for routine breast cancer screening in asymptomatic women, while diagnostic mammograms are used to evaluate breast cancer abnormalities or symptoms. So mammograms are typically performed by radiologic technologist who positions the breast on the mammography machine and takes an X-ray image. The images are then viewed by a radiologist who is specialized in interpreting medical images to identify any abnormalities or signs of breast cancer. However, mammograms do have limitations such as false positives and false negatives. So coming to our project, we have used two data sets, one based on mammography images and the other based on histopathology images, as they improve the accuracy and reliability of deep learning algorithm. Mammography images are widely used screening tool for breast cancer detection and are often the first line of screening for breast cancer. Mammograms can detect tumors and calcifications, which are early signs of breast cancer. And they can also identify other abnormalities such as cysts, benign tumors, or fatty tissue. However, mammography images have limitation in terms of specificity and sensitivity, as they produce false positive or false negative. False positive has said it indicates the presence of breast cancer when it is actually not present, leading to unnecessary biopsies or surgeries. And false negative result occur when mammograph misses a breast cancer, leading to delayed diagnosis and treatment. So we are using histopathology images also, which on the other hand are obtained through examination of breast tissues samples under a microscope. They produce a more detailed view of the breast tissue and allow for the identification of specific cell types and structures, which can help diagnose the presence of breast cancer and its characteristics. So by combining the information obtained from both mammography and histopathology images, deep learning algorithm can potentially improve the accuracy and reliability of breast cancer detection. The algorithm can learn to recognize patterns and features in mammography and histopathology images that are indicative of breast cancer, and they can potentially detect abnormalities that may be missed if either of the dataset is used alone. Overall, using multiple datasets can always provide a more comprehensive view of breast cancer and potentially improve the accuracy and reliability of deep learning algorithm in detecting and diagnosing breast cancer. So with this, I finish off my part and my teammate Aman will take over.
Thank you, Kamna, for explaining our project and how we are going to proceed. Good morning, everyone. Myself, Aman, and now I am going to explain our working on the Western breast cancer dataset, in which the features are extracted from the image dataset. So our objective was to build a model that can accurately predict whether a breast mass is benign or malignant, based on our 32 component features like texture, concavity, and smooth, and many more features from the digitized image of a fine needle aspirant of a breast mass. To begin with, we imported the necessary libraries and loaded the dataset. We then perform a data pre-processing by dropping irrelevant features and extracting the null value. We also visualize the dataset by creating a bar graph and showing the number of benign and malignant cancer type, as well as the scatter plot for our feature and diagnosis, as you can see on our screen. This is the scatter plot, and so this allows us to gain a better understanding of a data and identify any pattern or trends that could be useful for our model. So next, we address the issue of skewness in our data. So skewed data can lead to biased result and poor model performance. So we took the step to remove it. We used a log transformation for feature with value outside the range of 2 to -2 and printed the unscrewed value after transformation. Here is our unscrewed value. This helped to normalize the data and improve the accuracy of our model. Moving to our model building phase, we split our dataset into training and testing. We also use the ANN, artificial neural network, with 3-layer and Adam optimizer for our model. The Adam optimizer is the stochastic gradient descent optimizer algorithm that is used to update the network weight based on our training dataset. We trained a model for our 50 epochs, meaning that we went through the entire dataset 50 times, updating weight in each epoch. This helped the model to train and improve its accuracy over time. After After training the model for 50 epochs, we achieved the validation accuracy of 93% and validation loss of 25%. This means that our model was able to correctly predict a type of a breast cancer with accuracy of 93% and model loss with minimizing to 25%. To visualize the accuracy and loss of both the training and validation data, we create a graph. So this is our graph. It's showing our accuracy and loss of validation and training data set. In conclusion, to our, like this part, our data pre-processing and visualization and addressing skewness is improving the accuracy of our model. We were able to achieve the high level of accuracy in predicting the type of breast cancer using the ANN model with 3 layers and Adam optimizer. So this is from my side. And now my further explanation, my teammate Chinmay will continue.
I'm Chinmay, and in this part, we explore histopathology images for improvement in breast cancer detection. Let's understand what histopathology actually means. Breast histopathology is a medical field that involves the diagnosis and treatment of breast diseases by analyzing breast tissue samples. The diagnosis is made by examining the tissue samples under a microscope to identify the presence or absence of certain abnormalities. In recent years, the use of AI and machine learning techniques has become more prevalent in this field. With the help of these techniques, it is now possible to automate the analysis of breast tissue samples and improve the accuracy and speed of the diagnosis. The background of our project focuses on invasive ductal carcinoma, also known as infiltrating ductal carcinoma. It is cancer that begins growing in a milk duct and has invaded the fibrous or fatty tissue of the breast outside of the duct. Invasive means that the cancer has invaded or spread to the surrounding breast tissues. Ductal means that the cancer began in the milk ducts, which are the pipes that carry milk from the milk producing lobules to outside. Carcinoma refers to any cancer that begins in the skin or other tissues that cover internal organs, such as breast tissue. Over time, IDC can spread to the lymph nodes and possibly to other areas of the body. IDC starts in the cell that line a milk duct in the breast, breaks through the wall of the duct, and grows into the nearby breast tissues. At this point, it may be able to spread to other parts of the body through the lymph system and bloodstream. According to the American Cancer Society, about two-thirds of women are 55 or older when they are diagnosed with invasive breast cancer. The problem which we focus on this in this project and that arises is with this is that more women are diagnosed with breast cancer than any other cancer besides skin cancer, and as with any breast cancer, there may be no signs or symptoms. IDC is the most common form of invasive breast cancer and presents around 80% of these cases. So in the first part of our project, we talked about mammograms. A mammogram may reveal a suspicious mass which will lead to further testing, including biopsies, which involve taking out some or all of the abnormal looking tissue for examination by a pathologist. Histopathology, on the other hand, is the microscopic examination of breast tissue samples that have been surgically removed or obtained through a biopsy. The tissue is examined by a pathologist who analyzes the structure and composition of a tissue to diagnose or rule out breast cancer or other breast diseases. Basically, it can provide a more definitive diagnosis, but it requires a tissue sample and a trained pathologist to interpret the results. This is the reason why we took histopathology for our final review. So our data set which we use is a breast histopathology image data set provided by Kaggle. The dataset consists of 162 whole mount slide images of breast cancer specimens scanned at 40 times of the image resolution. From that, 3,83,171 patches of size 50 x 50 were extracted, out of which 1,91,577 are of IDC negative and 1,91,594,000 are of IDC positive. Our idea is to feed these pictures into an algorithm which would be able to classify whether invasive ductal carcinoma is present in an image or not. So the first part of our model building is to prepare our data for processing. So we first import all the possible libraries which are necessary for our project. Then we start by installing the Kaggle API by running pip install Kaggle. The next three lines create a directory called .kaggle in the user's home directory and copy a Kaggle API token called kaggle.json into this directory. This is a personal token API which we took from our Kaggle profiles. And finally, we download the required dataset. Now in this case, We then create a directory for all images using the osmkdir function. The next three lines create two subdirectories inside the all images directory using the os.mkdir function again. This creates a subdirectory named 1 inside the directory, while the other line creates a subdirectory named 0. 1 and 0 directories store images of malignant and benign tissue samples respectively. Now, what we want to do is we want to create a data frame for the image formation. This code is used to create two Panda data frames from list of images file names in two separate directories. Which are created above and then combine them into a single data frame. The first two lines of code function to get list of all the files in the directories respectively. These lists are assigned to image list 1 and 0, which are the benign and malignant. And the next two lines of the code here, they create two Panda data frames, and from these list of image file names, the concatenation function concatenates data frames along a particular axis, which in this case, we have taken the default axis of 0, which corresponds to stacking data frames vertically. We have visualized the data frame which we have created, and we also put in some functions in which these functions, the extract patient ID function takes a string as input and splits it using the underscore symbol as a separator. It then selects the first element of the resulting list and assigns it to a variable patient named patient ID. The function returns the patient ID, and the extract target function also takes a string as input and splits it using the underscore symbol as a separator. It then selects the fifth element of the resulting and the sixth character of that element, and it assigns it to a variable named target. The function returns the target. Results are assigned to a new column named patient ID and target respectively. This is what we use the functions for. This is a simple visualization of how our benign and malignant tissues are distributed. So in this case, we split the data into three parts: a training set, a validation set, and a test set. Then the train test split function is called twice on the data frame which we have made with different values for the test size parameter. The test size parameter determines the proportion of the data that should be allocated to the test and validation sets. The random state parameter is set to 42 to ensure that the splits are reproducible. The stratify parameter is set to y to ensure that the distribution of target values in the test and validation sets is similar to that in the original data frame. Here we have again used the df.value and we have visualized the benign and malignant distribution. So in this case, to this function we have made, and the use of this function is to, it takes a single argument, which is a value from the image ID column of the df.data frame. It first creates two lists of image ID values from the df_val and df_test data frames, which we have created before. Then it checks if the X value is in either of those lists. Pertaining to this, whatever result it is, then added it is in the data frame. The same process is repeated to create the validation directory and test directory directories. After this, subdirectories for the different classes of images are created. In this case, two classes are present, which are class 1 and class 0 as discussed before. Basically, this code sets up the directory structure necessary for organizing the image data into training, validation, and test sets for further processing. After this, we copy the images from the original directories into the new directories created earlier based on the respective data splits, training, validation, and testing. And we try to visualize and see the count of how many validation and train and testing images are present. After that, in this case, we create augmented images from the images in the train directory 1 and the train directory 0. Augmentation, we have done augmentation because it is a technique which is used to increase the size of the training data by applying different transformations to the images, and it helps reduce overfitting and improve the performance of the model as well. So we used augmentation so that we can get better results. From here, Chandan will continue.
Hi, Chandan here. I'd continue our presentation. So, in this code, we are defining the paths to the direction that contain the training, the validation, and the testing data, which are previously created by splitting the original data set using this function from the scikit-learn library. the train steps and the validation steps are the variables that represent the number of steps required to initiate through the entire training and the validation data sets respectively. Going on to the next one, this help us to display the random sample of 25 images from the training data set along with the corresponding labels. The following code which we have applied here loops through the first 25 images in the batch and displays each image along with its label. If the label is 0, the text IDC is printed as negative, and if it is 1, it is printed as IDC positive. The printing statement, a dictionary that maps the class name to the corresponding integer index. In this case, since the problem is a binary function, IDC positive and IDC negative, the dictionary will have two entries. The class weight is a parameter used in machine learning algorithm that assigns a weight to each class in the dataset. It is used to balance the combination of each class to an overall loss function during training. This means that the model will treat both classes equally during the training. Um, the CNN architecture using the Keras sequential model, the architecture consists of series of convolution 2D layers, the max pooling 2D layers, and the dropout layers. Here is the breakdown would be like the first layer is the convolution 2D layer with the 16 layers of size 3 by 3, and the activation function is ReLU. The next two layers are also convolution 2D layers with 16 filters of size 3 by 3, and the ReLU is the activation function, but with the same padding. The max pooling 2D layer with the size of 2 by 2 is added to reduce the spatial dimension of the feature map. The next three layers are similar to the previous convolution 2D layers, but with 32 layers of size 3 by 3 and ReLU function. Later, another max pooling 2D layer is applied. The next three layers are again similar to again previous 2D layers, but with 64 filters of size 3 by 3 and ReLU function, activation function. A dropout layer with the rate of 0.35 is added to reduce overfitting. The dropout layer with the rate of 0.5 is added between them. The final dense layer has 2 units and uses the softmax activation function to output probabilities of each class. The next code compiling the Keras model called the backbench uses the compile function. It is used to configure the learning process of the model. The loss function is used during training. In this case the binary correspondency is used since this is a binary classification problem. The optimizer function is used to optimize the training here. Here the item function is used, which is popular among the optimization functions algorithms. Mm, Coming to the next part, the model checkpoint callback function is used to save the best performing model during the training process. The verbose parameter determines the outcome of uh, lo of the logging output. The history benchmark is a function returned by the fit generator method which contains the information of the training history of the model. The epochs parameter specifies the number of times the model will be trained on on the entire data set. The next two lines explains about the computing and printing of the two different accuracy scores for classification problem. It returns the average of recall obtained on each classes. The 1.3f formatting specifies that the resulting floating point number should be printed with the 3 decimal places. The next code defines a function called matrix that computes the function matrix for a binary classification problem. The resulting matrix is then plotted using the plot command from the matplotlib module. The interpolation parameter specifies the interpolation method used to display the matrix, and CMap specifies the color map used in the matrix. Mm, the classification report, which contains the variety of matrices such as the precision, recall, F1 score, and the support for classification model precisions. The classification report function is used to compute and print the classification report for each predicts for the predicted values y predict, and the true labels is y true, with the target name as negative and positive, or positive and negative. The resulting report contains information on the precision, recall, F1 score, and support each other classes, as well as the macro and weighted average across all the classes. This module over here represents the graph which we have obtained from training and the validation from of the training and validation accuracy and the training and validation loss. This defines us about the graph, and we can see that the problem doesn't the graph doesn't seem overfitting, and this is the best we could have got for the training which we have obtained for the training which we have done, and the accuracy has been mentioned above epochs. Hmm. For each image in the loop, its label as printed is either IDC negative or positive, depending upon the ground truth label. The loop then proceeds to the next image until all the images in the batch have been processed. Over here, we could see that this is represented as IDC negative with the predicted negative value as 99.87 and the positive standing as 0.13. So this means that the patient over here is breast cancer is tested as breast cancer negative. Moving, if you can uh, move down to the next diagram, you can see that the predicted negative possibility probability is 99.32 and the positive is 0.68, which also specifies that the patient is tested negative for breast cancer, and therefore we have IDC negative. The next sample predicts the same with different number of with different probability cases, being the negative as higher from the positive one, and therefore the IDC is specified as negative. The next image represents the same with different numbers, standing as 88.37 as negative, and the positive standing the remaining. Therefore, this is also represented as IDC negative. Coming to the next one, the IDC is positive over here, since the positive probability is 75.19 and the remaining is the negative one. Obviously, the positive probability is higher than the negative one. That's why here it is represent here the breast cancer detection for this case is IDC positive. To the next one, here also the negative value is much higher than the positive one. Therefore, this is tested as negative for the breast cancer. The same goes with the other one where the negative stands as 91%. And the next one, we can see that the IDC, the positive value is 71.88, which is represented as 1 in the binary case, and therefore the IDC is positive and the patient is tested positive for the breast cancer. Um, Breast cancer detection models can be used in a variety of ways to help with early diagnosis and treatment of diseases. Here are some of the use cases. Mammography implementation. One of the most common uses of breast cancer detection model is to assist radiologists in implementing mammographs. The models can highlight suspicious areas that may require further investigation, allowing for earlier detection and treatment of breast cancer. The risk assessment. The breast cancer detection models can also be used to assess a woman's risk of developing breast cancer. By analyzing a woman's medical history, family history, and other risk factors, the model can provide an estimate of her likelihood of developing the disease. Personalized screening. Breast cancer detection models can also be used to develop personalized screening plans for the woman based on their individual risk factors. This can help to ensure that women receive the appropriate screening at the right time. The treatment planning. Breast cancer detection models can also be used to help plan treatment for women who have been diagnosed with breast cancer. The monitor response to treatment. The breast cancer detection models can also be used to monitor how well a woman is responding to a treatment. By analyzing images and the other data, the model can provide information on whether the tumor is shrinking or growing, allowing doctor to adjust the treatment plan as needed. In conclusion, um, our breast cancer detection model has shown promising results in providing the accuracy and efficiency of the breast cancer diagnosis. Though the use of advanced algorithms and deep neural networks, the project has demonstrated the potential to significantly improve early detection and personalized treatment for breast cancer. The project involved several key steps, including the data collection, pre-processing, model training and validation, and model deployment and evaluation. During the training process, the deep learning algorithms were trained to identify patterns and features in medical images that are associated with the breast cancer. The resulting models were able to analyze new images and provide accurate and reliable diagnosis. Overall, the project has demonstrated the potential for breast cancer detection to improve patient outcomes and reduce the workload of the medical professionals. However, further research and development are needed to fully realize its potential and address its limitations. Further projects could explore ways to improve accuracy and efficiency of the deep learning breast cancer detection, as well as its ability to detect breast cancer in diverse population, and in the case where the cancer is located in less viable areas of the breast. This is us, a group completing the project for the breast cancer detection. Thank you.